Okay, this is version 2 of the linear programming lecture on feasible and optimal feasible and all that stuff. Why is this version 2? Because version 1 somehow did not record. So I will give the lecture again because I know several people are taking this class remotely or have conflicts at the same time. However, in the interests of my sanity, I will not give the lecture exactly as before, but we'll do it at a little bit of a faster pace. So we start off by talking about how going from feasible to feasible basic is really good in that it kind of limits the set of solutions we're looking at. And the goal is that instead of looking at the whole space of feasible solutions, it's sufficient to just look at the space of basic feasible. And we're going to see the same thing is true for optimal solutions, that if there is an optimal solution, then there's a basic optimal. What's nice is this is a great way to review the proof we did from linear algebra before. So I called it a theorem before. I'm a little bit upset because I'm giving this lecture again, so I'm going to downgrade it to a lemma. If there exists optimal, then there exists a basic optimal. And I started off by asking the class, how would we go about proving this? And there were great suggestions that we should first say, well, let's assume we have an optimal that's not basic. So assume x is optimal, but not basic. So what that means is the corresponding columns to the entries where x is non-zero are linearly dependent. Okay? How else can we go from this point onward? Well, the suggestion was, let's argue as we did in going from feasible to basic feasible. Let's take some kind of minimality property. So we'll assume x is minimal, so fewest non-zero entries. And so what we have is we have xj1, aj1, plus dot 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 plus xjk, ajk equals b. The entries of x prime, so the xjls are greater than or equal to 0. That's what it means for x to be basic, for x to be feasible. Now we want to show what happens because it's not basic. Because it's not basic, the columns are linearly dependent, so we can find some numbers gamma j1 through gamma jk such that that linear combination is equal to 0. And we talked at length about why this is the 0 vector and not the 0 number. Because I'm doing this again, I'm not interested in doing it again, so we'll just leave it like that. And so we have this linear combination. We can multiply through by lambda, and it's still going to equal 0. Lambda times 0 is still 0. And of course, the 0 vector. And so now this is very similar to how we did the proof before with the basic feasible. And so what we're going to do now is we're going to subtract, and we'll get xj1 minus lambda gamma j1 aj1 plus dot 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 plus xjk minus lambda gamma jk of ajk equals b. So what's nice is we formed a new solution. This is still going to be a feasible solution in that it's going to satisfy the original constraints. But what else will we have? Well, the other stuff we're going to have is that it is going to additionally be an optimal solution. And so the optimal solution is not clear immediately, so we're going to have to do a little bit of work on that. Why is it feasible? Well, it still satisfies the initial constraint here, that ax equals b. But remember, to be feasible, it's not enough that ax equals b. We also need, more as importantly, that the entries of x are non-negative. And this is part of the canonical representation that we're choosing for all of our solutions and for all of our formulations of the problem. So we talked at length earlier in the semester as to why, given a linear programming problem, we can always convert it into canonical form. This is one of the dividends, is we can assume we're in this form, we can argue along the lines, we need each of these coordinates to be non-negative. Well, we know the x's are non-negative, and we know when lambda equals 0, everything is fine and everything here will be positive. And so we need more than just non-negative, we need positivity. All right, well, the x's, I'm sorry, it's been a long day, as you can probably tell. So the xj1's positive, xj2 positive, xjk positive. If I take lambda equals 0, everything is positive. And so now, because it's positive when lambda equals 0, by continuity, I can increase or decrease lambda by a small amount and still have all these entries be positive. So when we look at this linear combination, not all of the gammas are 0. Without loss of generality, we can assume if we want gamma J1 is non-zero, we can assume it's positive. Always multiply through by -1 if you need to. Relabel the indices, standard tricks of linear algebra. And so when we look at this, eventually we know we will be able to increase lambda to the point where one of these entries will become 0. At most, we do it as xj1 divided by gamma j1. But maybe several of them become 0 at the same time. It doesn't matter. All that matters is that for lambda sufficiently small in absolute value, this new x vector is still feasible. So we get a new solution. We'll call it x prime lambda. The prime is because we only care about the entries that are non-zero, and the lambda because we've now tweaked it a little bit. And so this is going to be feasible. Okay, so now we have a feasible solution. The question is it optimal? So this is where things differ from what we did on Friday. On Friday, we just cared about, do we have a basic solution? Do we have a basic feasible solution? Do we have a feasible solution? Here, it's not enough to have a feasible solution. Our solution must also be optimal. Why? Well, the goal is to show that if x is optimal but not basic, then there's a contradiction. Well, if this new vector is not optimal, then that could be the contradiction, that it's not optimal. So we want to show that this is optimal as well, and that we can choose lambda so that we have one fewer coordinate being non-zero. And then that will violate the minimality. So we talked at length about how you can't be smaller than minimum. You can be equally minimal, but you can't be smaller. So that's the contradiction we're going for. All right, so we have our new vector over here. And then what we're going to do now is we're going to look at the new cost. So I'll keep all this stuff over here. So the old cost was C prime transpose x prime. The new cost is C prime transpose x lambda prime. And that's going to be C prime transpose x prime minus lambda C prime transpose, and we'll just call it gamma, where gamma is coming from the stuff over here. Well, there are three cases for this quantity. We talked at length about the possibilities. Unfortunately, we can't just look at the problem and see what this is. We don't know, but we can investigate the cases. So case 1, C prime transpose gamma is greater than 0. Case 2, C prime transpose gamma is less than 0. And not surprisingly, case 3, C prime transpose gamma equals 0. Well, if this is greater than 0, then we choose lambda to be a small positive number, and this will be a negative quantity over here. We will subtract a negative quantity from the old cost, and the new cost will be smaller. So this violates x prime optimal. All right, well then what if C prime transpose gamma was negative? Well, if it was negative, and this is negative, we now take lambda to be a small negative number. And by taking lambda to be a small negative number, we get a new cost that is going to be less than before. And again, violates x prime is optimal. So the only case that's left is that C prime transpose gamma equals 0. So this must hold. And so this is 0, and it's 0 the number. So what that means is this x lambda prime, not only is it feasible, it's also optimal. And that's exactly what we needed for the proof. So now we have a new solution. It's feasible, it's optimal, and if we increase lambda sufficiently large, eventually one of these coordinates will become 0, and we will now have fewer non-zero coordinates. That violates minimality. That's our contradiction. So again, lots of ideas here, very similar, not surprisingly, to the proof on Friday, that if we have a feasible, we have a basic feasible. So the question is, why do we care about something like this? And so we talked about putting ourselves in the role of a Williams admissions officer. We have lots of people applying to Williams. We're trying to sort through the list, trying to see who we want to admit. It would be wonderful in the sense of their jobs if everybody went to the same school, had the same teachers, did the same sports, did the same extracurriculars, had parents with the same income. Actually, if you had the same parents, it would be even better. But we're not going to get something like that. We're going to get lots of differences, and we need to figure out which differences really matter, which differences don't. We want to try to find a faster way to go through the space. If we try to box everybody off into different bins, the more categories and features we have, the fewer elements we'll have in each bin, and the less predictive they'll be. So we talked a little bit about left-handedness. Does left-handedness really matter in terms of trying to predict someone's success at Williams? We can come up with many ridiculous things that admissions quite rightly does not look at in trying to determine who will be successful here, who should come here. So the whole idea of this idea of approaching the problem by looking for basic feasible and then basic optimal is that we're winnowing the space that we need to study. And rather than looking at the entire space, we're now looking at a smaller restricted space. Okay. So of course, in everything we're doing here, the question is, can we make this explicit? Can we make it constructive? Fortunately, if we start off with a feasible solution, we want to make it basic feasible, there's an avenue. Look at linear combinations of columns, and somehow, using the linear combinations of columns, take one away and remove it. Now this gives us the option of which one should we take away? And that will be an interesting question which we'll get to when we get to the simplex method, and will be related to how quickly and how fast the algorithm runs. So what I want to do now is I want to do the Euclidean algorithm. And so again, the question is, well, why would we be doing the Euclidean algorithm in a class like this? This is a class in operations research. Well, the reason I want to do the Euclidean algorithm is I'm a number theorist, I can't help it, I like to do number theory, but also there's a lot of features about this problem which will do a really good job of explaining what's going on with operations research. In particular, I want you to always be at the point now where whenever you see something new, you think about, how can I do this efficiently? How can I do this well? Is this running well? What is this giving me? So the basic building block in number theory are the primes. And we joked about whether or not there are infinitely many or only finitely many. It doesn't take too much work to start generating a few on the list. And so one of the oldest proofs, copyright has expired many, many years ago, all the way due to Euclid, there are infinitely many primes. I'm not going to give the geometric flavor of the proof, I'm going to give the more modern day version. And so it goes as follows. Assume, so I'll go theorem, this is definitely with the theorem, not a Euclid. There are infinitely many primes. And so it's a proof by contradiction. So assume not. And let's look at the entire list of primes. Let's say P1, P2, all the way up to Pn. So if there's only finitely many primes, we can list them all. Let x be the product of all the primes plus 1. So the first prime is 2, the second prime is 3. So this is going to be at least 7. All right, so we have two possibilities. Either x is a new prime, or x is not a prime. And again, a prime is a number that is divisible only by 1 in itself and is at least 2. So we do not consider 1 prime. The reason we don't consider 1 prime is we want a property called unique factorization to hold. Every number can be written uniquely as a product of primes. 6 is 2 times 3. Can't write it as 2 times 5 or 2 squared or anything like that. If 1 were prime, we would have many ways of writing numbers. So case 1, x is prime, we're done. Our list is incomplete. We found a new prime. All right. Case 2, x is composite. Well, if it's composite, it must be divisible by a prime not on our list. If this was a number theory class, I would prove this. I think we can just assume this and move on, especially since I don't want to talk for too long today because I've got to have this uploaded before I go. So it's composite. Could it be divisible by P1? No, because if I try to divide by P1, I get a remainder 1. Can it be divisible by P2? No, I get a remainder 1. All the way up to, can I divide by Pn? No, remainder 1. So it's composite. So there exists a new prime P such that P divides x. And so in both cases, we see that our list is not complete and that there is a new prime. All right, now that we have this, the question becomes, what else can we glean from this? Do we have any idea of how quickly this is going? So when you're trying to look at how many primes, a natural thing is to count them. So we know that there are infinitely many primes. So the key thing is to let pi of x be the number of primes p less than or equal to x. The famous prime number theorem says that pi of x is approximately x over log x as x gets large. It was proved in 1896. This is a great theorem, extremely important in mathematics, extremely important in number theory, highly celebrated, and in fact I got to go to the 100th anniversary of the proof of the prime number theorem in 1996. It was the first conference I went to. This is the true answer. This is the true growth rate for the primes. What if we look at Euclid's argument? Well, in terms of seeing how large things could grow, the worst possible case is if every single time we're in case 1, where our number is prime, so we've increased by the maximum amount possible. Let's see what we would get. We start off with 2, so I'm going to have to erase this for space. So we start off with 2. We add 1, we get 2 plus 1 is 3, which is prime. Then 2 times 3 is 6, plus 1 is 7. Then 2 times 3 times 7 plus 1 is 43. It turns out these are all prime. And we can keep going and arguing along these lines. So if we keep going along these lines, the next one would be 2 times 3 times 7 times 43 plus 1. And this is approximately 42 times 43 plus 1. Actually, not approximately, it is 42 times 43 plus 1. So this is approximately 43 squared. So what we see is as we keep going down, if we're always in case 1, every step we essentially square how big our number is. 2 squared is about 3, 3 squared is about 7, 7 squared is about 43, and so on and so on. So if you try to play with this, you see that this is growing very fast. And so in terms of, if we want to get all the way up to 2 to the 20th, where we go 2, 2 squared, 2 to the 4th, 2 to the 8th, 2 to the 16th, and the next one would exceed 2 to the 20th. Note, 2 to the 20th is 2 to the 10th squared. 2 to the 10th is approximately 10 cubed, so this is about 10 to the 6th. So this would give us 1, 2, 3, 4, maybe about 5 or 6 primes less than 10 to the 6th. If we went all the way up to 2 to the 32, we would replace this with the 32. This would be 10 to the 3 to the 2 to the 10 to the 3.2. 2 to the 10 is about 10 cubed, so this would be about 10 to the 9th. And this just shows you how bad Euclid's argument is. It does give us a lower bound for the number of primes. It gives us the number of primes at most x is greater than or equal to some constant times the log base 2 of the log base 2 of x. So this is a very slowly growing function. But it does go to infinity, it does give us a growth rate, but it doesn't give us a good growth rate. It's nowhere near the truth. Now there's something interesting if you look over here. I said the worst possible case is if you're always in case 1. 2 plus 1 is 3, prime. 2 times 3 plus 1, prime. 2 times 3 times 7 plus 1, prime. Now, if we look at 42 times 43 plus 1, it turns out that this is not prime. There's lots of ways to see this. The easiest, of course, is to just multiply it out and factor it. It's not going to be divisible by 5, because it's going to be 6 plus 1, so it's going to have a remainder of 7. You can do a little bit of checking to see it's not going to be divisible by 11. The first prime it's divisible by is 13. One nice way to see this is 42 is equal to 39 plus 3. So if I look at just the remainder by 11, this number is really the same as, by 13, this is the same as 3. 43 is really the same as 4 mod 3. And 3 times 4 plus 1 is congruent to 13 mod 13. So this number is going to be a multiple of 13. So what this tells us is that the sequence, unfortunately, is very strange. The next number here is 13. So we've got 2, 3, 7, 43, 13. The numbers are hopping around. So in terms of what the numbers equal, things get very interesting. So the next numbers in the sequence go 2, 3, 7, 43, 13, 53, 5. So we finally get 5. 6,221,671, 3870, 918, 3810, 571, then 139, 2801, 11, 17, 5471, and the next number is huge, 52662,739, 23,003, huge number, 306936516062009, 37. So the sequence is all over the place. And this is one of the strange things. This is called the Euclid-Mullen sequence. We do not know that many terms in it, so these are the only known elements right now in the sequence. So I'm trying to see how many it says. Does it say how many terms there are in the sequence? Well, we can just quickly count them out. So I will leave that as an exercise. This is on the order of 40 terms in the sequence. So there's lots of questions you can ask in a situation like this. So what kind of questions can you ask? You can ask, is every prime number hit at some point in the Euclid argument? So when we do the Euclid argument, we always see what's the smallest number that's prime that's not on a list and add the list. Will every number be hit? So at first we lost 5, but we then eventually got 5. We didn't have 11. I think we went back and got 11. Let me double check. We do have 11. We have 17. I don't see 19 quickly. Nope, we get 19 if we go down far enough. And so the question is every prime hit eventually? What other questions could we ask? Well, not just is every prime hit, but how far do you have to go before you hit the number? If I give you a number p, can you give me some estimate as a function of p of how far I must go before I hit that prime? What we could do is we could try to tweak the argument. Instead of putting in the smallest prime that doesn't divide a number, the smallest prime that divides a number, what if we put in all the new primes? That would help us get numbers a lot faster, or maybe then there would be some payback later. So lots of great things you can investigate, huge number of open problems here. So again, this is not a standard topic to include. As I'm recording the lecture again, it's like, do I really want to say this again? And the answer is yes. Why do I want to say this? Because one of the purposes of this class is to get you to think about things efficiently. No matter what it is in life, can you do it better? What's the bottleneck? What's the difficulty? And over here, when we look at Euclid's argument originally, and this is something I hope many of you have seen before, we don't necessarily think about how fast it is, about how quickly is it. Does it generate infinitely many primes? And the answer is yes. But then how rapidly does it grow? And the bound is very bad. Does it hit every prime? Again, open question. So thank you, and I do apologize for the shortness of this talk. You can do a very interesting calculation as to, we did this in 22 minutes, and the class today was 50 minutes, so why is this so much shorter? Part of it is the lack of desire of doing the whole lecture again very slowly. Part of it is, there were great questions in class, which helped me refocus the lecture and choose exactly what to emphasize. Part of it is, the more times you give something, the more efficient you get. Have a good day.